So, okay, I wanted to touch up a couple of little points on Gauss's law, and I hope you all read that message I sent that we're going to have to speed up because the lab next week concerns circuits, and I don't want to go in there and not know what you're doing. So we'll try to begin circuits on Friday. Today, I want to finish up a couple of little points on Gauss's law, particularly in conductors, and then move on to electrical potential and potential energies. So you recall that Gauss's law said that if you have some net charge inside a region, you could have plus and minuses, pluses like that, whatever you have. If you put a bubble around it, of any shape, as well, if you encompass all of them within a surface, the net amount of electric flux coming out of the thing, which we define as this is the electric flux, and if you integrate it over the whole bubble, then it'll tell you the net amount of charge. Q the net, important, net inside. For example, if I took this radio and I put a bubble around here, this is not electrified. It's got a lot of plus and minus charges in it, but I'll get zero electric field outside because the plus is equal to the minus, so it's the net. So in a case like this, the net is the way I drew it, one extra plus. So I would have a net outflow of lines from this particular object, these three. So that's an important point. It's the net charge inside. And this is so fundamental a law that it even works when you advance to the level of special relativity. This law still holds. Now we derive it on the basis of Coulomb's law. Remember, we derived that if you integrate the electric field to a single point charge, what you have to put in with the electric field is kq over r squared to get the result when you multiply by the area, the area, 4 pi r squared. R squared. The r squared will cancel out, and you end up with that the integral over this area is proportional to q. We change the notation and call it epsilon naught. And in statics, just throw this in. In statics, the electric field is perfectly symmetrical and radial because you have a point charge. Now in relativity has to do with moving charges. And it turns out the electric field moves at the speed of light. So if you can get a charge moving at a very high speed, it's kind of catching up with its lines. So Coulomb's law, namely that the electric field is a simple kq over r squared, and it's symmetrical in all directions, it won't be symmetrical anymore because it's a direction of motion. Right? So that Coulomb's law doesn't work when you go to high speed relativity. But Gauss's law continues to hold. That's why people are so enamored of Gauss's law, because you can still make a bubble around it. And the number of lines coming out, even if the lines are moving, and shorter in one direction because you sort of get something like this with a moving charge. You sort of like a wake of electric field. If the thing is moving this way because it's catching up. So it's not exactly symmetrical. It's a little, or it can build up like a shock wave because the waves in front sort of caught up with. So it's a little distorted from Coulomb's simple symmetrical picture because it's no longer symmetrical. There is a direction of motion. So that's why even the relativists use Gauss's law. But just to point that out, that it's given a lot of prestige, and that's why maybe it's an introductory text, although they don't make much of a reason why you bother with Gauss's law if you have Coulomb. Well, you've already seen that knowing Gauss's law allows you to solve certain problems very readily. The one I really want you to appreciate is the one of a sphere, where as you go further and further, let's say this is sort of idea of the meatball of charge, solid sphere of charge, as you go out in radius, you encompass more and more charge. So the field builds up. So the diagram for the electric field as a function of, well, let me do it perhaps this way. Starting out from the center, there is no electric field at the center of the meatball. Why? Well, all the fields are pointing in some direction, and they will cancel out right at the center. So the center is 0. But as I go out to a point, say here, I can draw a sphere around the center, and I capture the charge that's inside that region. And so the electric field flux coming out tells me there's net charge inside here. And as I make that bigger, I capture more and more charge, the field gets bigger and bigger. So the field rises actually linearly with the distance till you get to the surface. So this is E as a function of my distance r. Then once I get to the surface and if I make the bubble bigger, I don't collect any more charge because I've got it already, right? So then what happens is that just the bubble gets bigger, the area gets bigger, but the amount of charge inside stays the same. And so what happens is that the field, because the field is equal to Q inside over the surface area, once I'm outside, it's only the surface area that's increasing. I've caught all the charge rate, so that's constant, and you just go over the area. And then the area increases as 1 over r squared, and very likely, and very nicely, it goes as 1 over r squared. Does that make sense? That's the way it works. And the point is that this whole sphere acts as though it's a simple Coulomb field centered out at this distance here. It's the same as the Coulomb with all the charge at the center, because it's the same exact law. So that's a very nice law because it simplifies the problem. If I have a sphere of charge here, spherically symmetric, it has to be spherically symmetric. And I have another spherically symmetric charge here, and I want to know the forces between those. I can treat it as though all the charge were at the center. I don't have to worry about every little charge pulling on every little charge here. No. I just take this, put all the charge at the centers, Q1, Q2, and I treat it like a simple point charge acting on another point charge. That's a very big simplification, and it's accurate. I can't resist telling you that these do work for very symmetrical charge. And it's also true for gravity. Gravity has the same behavior, 1 over r squared. Gauss's law works for gravity as well. And you should know that if the thing is not symmetrical, then as you go around, here's the thing. Now let's make it unsymmetrical. This is the case for gravity too. Suppose you were prospecting for like oil. Now oil is unevenly distributed, so it breaks the symmetry of the Earth's gravity. So that whereas if you were flying along here, you'd expect the gravity field to be a certain amount. Gravity, of course, pulling inward. And at a certain, if you could keep the same height from the center, you'd expect as I go around the Earth that the gravity force should be the same everywhere at the same height. But if there are irregularities in the surface, in the density, or the mass is here, then the gravity field will fluctuate, depending on whether this is less massive or more massive. If you're prospecting for gold, large amounts of gold, enough to affect the symmetry of the surface, you would get more pull, the gravity would be greater. Because gold is not uniformly distributed, it's directly symmetric around the Earth. That's clearly, I mean, you have to go to California hills to find gold. But I read some while ago that they did this prospecting over Afghanistan. Now, how do you prospect over Afghanistan? There's a war going on there. You don't go and tap in the ground. They flew over it with these gravity meters. And they could detect variations which they could attribute to mineral deposits. And that's why there was a report in the newspapers that there's $1 trillion worth of mineral deposits in Afghanistan, found by this method, flying a very sensitive gravity detector over the surface and seeing the fluctuations due to the asymmetries, due to the oil, and I think there was a lot of lithium there. Lithium is very valuable for batteries these days, and lithium's light, so it affects things strongly, and other precious metals. So be aware that the Gauss laws work nicely for very symmetrical situations. If it's unsymmetrical, you can also get something out of it, perhaps. Okay. So that's a very important result, because a sphere is a very good approximation to a lot of things, like two atoms pulling on each other. The other case that I wanted to talk about a little bit further was the idea of a metallic surface of, well, pretty much any shape. And what happens if, for example, you put this in an electric field by some means? In other words, for example, I could just put a bunch of plus charges, say, over here on something. And, well, sort of like that plate. Well, I could do something like this. And so I create an electric field going from here to here. And I just put a lump of conducting material, conductor. So the electrons can move. And we've talked about this already a few times, namely, that it's the electrons that move, so they will be attracted to the plus side, and they'll leave behind the ions, the atoms from which they come, so that will sort of be plus like this. And it turns out that the charges will reside on the surface of the conductor. The reason being, I think I tried to say last time, was that if there were any field inside, then there would be a force on any charges, which would make them move. And what they do is move to situations such that they cancel out the field. And that's what's happened here. You see, when they move to the sides, what they managed to do, you see this field was here, and it's even here, but when the minus charges move here and here, they create a field this way, inside. And that field exactly cancels the field from the outside, so that the field on the inside is 0. So the charges will move and adjust themselves so the field is 0. The reason being that if it were not 0, they continue to move. So in the static condition, nothing is moving. We're dealing with electrostatics here. Nothing is moving, so the field inside the conductor must be 0. Now, that has some interesting implications, and these demos I've been bringing out so often to show the point. Namely, how does this Van de Graaff work? Remember, let's see how it's set up now. Right. Okay. Remember that this is just a bell to make sparks, wake people up. This one, there's this belt which is rubbed on down at the bottom. Charge is carried up to here, and I showed you before. There is again, you see these kind of brushes, like a little screen there, that's attached to this part, so that when the charges come up, there's a lot of negative charges, say, on the belt, and they want to get away from each other, so they can jump that little screen there. It gives them an avenue to escape onto this bell. Now, if the charges stayed on the inside, as the charges came up, they would already see somebody's already living there, and they wouldn't want to go onto the inside of the bell. But Gauss's law will tell us that the charges really go on the outside. So what happens is that I deliver charge to the inside, they quickly run to the outside, and leave the inside free of charge. So that when the next bunch of charge come up, they see, there's an empty bell, there's no charge there, and I can jump off and run to the outside. Right? So the inside has no charge, and the outside has charge, and that's why this thing works, because if this charge stayed where they landed, let's say on that screen, let's say on the inside, so much charge would accumulate that none would want to jump off the belt anymore. You get that point? So that's what Van de Graaff's bright idea was. Let me put this little screen on the inside, and I'll deliver charge to the outside, and that will, yes. Do I have to even do this? Do you want to see sparks again? You care? Do you want to see sparks? This may be our last chance to see sparks if I can get the thing back again. Oh, yeah. All right. All right. Just for fun. Wake up. Things that my hair stands up when I get near this thing. I don't know if you want to try. I drew a spark. All right. Oh, that's a pretty fat spark, huh? And it wouldn't happen but that the charge runs to the outside, and the new electrons can get off onto the inside of the bell. Enough already. So that's I think the most dramatic instance of how the charge does run to the outside, and it wouldn't. I could show you this one too very quickly maybe. Here's a solid metal globe with just a hole in it, and what we can do is put some charge on the outside of the globe and see if any of it goes to the inside. According to this thinking, the charge should stay on the outside. Even though it could conduct to the inside, it doesn't do it because of this rule that if I draw this surface here, oh, I didn't do this quite right. Let's see, this is uncharged supposedly. Yeah, okay, let me put this in here. And if there's any charge inside, it'll sort of go on that metal ball, and I'll be able to take it over and touch here and prove that there was charge inside. So let me do that. Let me first put some charge on the outside of the globe. This is an insulating rod, so the charge stays more or less where it goes on, and I sort of am wiping it off as though it were little guys here on the rod. But once they get on the globe, they'll run around. They can run around on the globe because that's metal, but on this is not. Okay, so, all right, now the first question is, did any of those guys that I put on the outside get to the inside? No. Let's try to see. I'll try to pull it out. Hopefully not touching the thing if I can do it. Not really. Okay. Now let me touch the outside and see if there's any on the outside. I may not have gotten any. No. Let me try again. Should be something here, unless the humidity pulls the charge off so fast before I can get to it. No, it's not working. All right, will everybody stop breathing? Well, it doesn't work for some reason. I don't know. But there's another trick that I wanted to do with you, and namely, the one we worked out. Namely, this is an electrical screening idea. If, for example, we had a radio, and we put it inside a metal sphere. Now, along comes, radio signals are electromagnetic waves, so it's an electric field, and it's varying, plus minus, plus minus. But when it comes to this sphere, let's say the field is this way, the electrons are going to run over here on the surface of the sphere and leave E inside equal to 0. So if E is 0, even if the field changes, E remains 0, and the poor radio doesn't get any signal because all it sees is nothing. So this would be screening, and that's the reason. For example, you come inside a building, you lose all your some buildings, you lose your cell phone connection, because that's also this. So first I wanted to try with a radio to see see if I have any connection here. I'm standing even near the door. There's not very good reception. Pardon? This is a wooden door. I don't think it should matter much. Doesn't matter. Does anyone want to hold the door open? That's it. All right. There may be more metal in it. It's pretty weak, I'm afraid. Ah. Well, I'm going to rush right out and do that. Okay. Now, here's the thing. Here's the thing I want to do. There is a stock demonstration where we put it in a kind of heavily screened box, and it kills the radio. But my question is, look, if I had what's a three? I'll think of it later. Three-letter word. Look, if you have a tight screen, granted this works and it kills the radio. On the other hand, if I make holes in the screen, suppose I make the wires really big. Suppose I have one wire in the universe. Will that stop the radio from going in? No. So thinking like a physicist, you would think, surely there must be some size that if I make the holes bigger, the radio wave will be able to get through, right? So that's what I got these chicken wires for. See, this is a rather tightly wound one, and so likely the radio waves would not easily get through here, but maybe, see, with holes like that, maybe they get through. Okay, let's just see. I don't know. Let's just try and see again.
Here's another long set of your favorite songs on 96.5 KOID.
Okay. Easy come, easy. Wow, that's better already. Shut her up. Okay. All right, so it doesn't get through this tight screen. Now let's see what about this guy. I'm not taking bets. No, doesn't get through that one either. I don't think it. By the way, if I put my hand in here, my hand acts as an antenna. And it comes. Oh. Because I'm conducting what the electric field's in. So I'm a little bit conductive. But okay, now we have, but this is radio waves. Now the point is radio waves are rather long waves, and so to a long wave, I guess this screen, even with its larger holes, still looks like a pretty solid screen. Like if it's a very, very long wave, very annoying. But I just want to try this for fun with cell phones. With a cell phone, the wavelength is shorter. So it's possible that whereas the cell phone might get through these holes because the wavelength is shorter, and so if you're a little guy, you can get through the holes. If you're a big long wave, you might not. So how many bars? Three bars. Okay. Well, maybe we'll just use your testimony, right? Unless you want to, we could call each other. That would be another way of saying it. But she's going to put that in there and see how many bars show up. One. Okay. Okay, that's a tight screen, and it knocked it from 3 to 1.
Oh, no service.
No service at all. Knocked it off. Okay. Let's try that one just for fun. I'm curious. Now it might show something. Service, come back.
It's got 2 bars.
Okay.
Still got all 3.
Still got all 3. Well, that kind of proves it. That's nice. So it worked. In other words, with cell phones, you have these microwave antennas. You see these dishes where they transmit the cell phone thing. It's a short wavelength. It's about like that. It's microwaves. Micro meaning sort of like a wavelength on your microwave oven, which is about that long. With radio waves, are many meters long. So to a radio wave, this looks like a solid screen because it's very. It's sort of like a giant stepping on this would think it's solid, whereas an ant would not. So that's. I just wanted to bring that up because, again, I think in true life, you won't remember all these formulas and everything a year from now or an hour after the final. But let's be frank. But the thing is that I want you to get some feeling for the simple physics idea that things on the same scale tend to interact with each other strongly. It's something you really know. In other words, if you're walking and it's a rocky thing, if the rocks are very big, it's not so bad. You can walk around the rock.